Now we're going to look at integration using the reverse chain rule. Let's go back and revisit the chain rule. So we use the chain rule to differentiate a composite function. So if we had f of g of x and we wanted to differentiate that function, we would differentiate the inner function first, and then we'd differentiate the outer function and apply that to g of x. Let's look at this in context. So if I had, let's say, y is equal to x squared plus 3 all to the power of 4. If I differentiate that, I'm going to start off by differentiating the inside function, which is going to give me 2x. Then I'm going to differentiate the outer function, which is going to be 4 to the front and reduce the power, and back in with my original function. And there I have my final answer, is equal to 8x, x squared plus 3 all cubed. Now just to take an example from trigonometry, if let's say I had the function y is equal to, I don't know, cosine of 2x minus 1, again applying the same rule, differentiating inside the function first is going to give me 2. Differentiating cosine, well, cosine differentiates to give me minus sine, and this is applied to 2x minus 1, and there we have our final answer. What we're looking at when we integrate using the reverse chain rule is looking at a line like this. We want to try and get back to our original function. What we're trying to do here is have a best guess. So let's go off and look at an example. So here I have to integrate sine. Well, I know it's useful for me when I'm doing trigonometry to possibly write down my list of differentials and integrals. And remember that if I am moving down my list, I am differentiating, and if I am moving up my list, I am integrating. So I think to myself, what would be a sensible guess at the integral of this function? A sensible guess would be that sine would integrate to give me minus cosine. So my guess is that this function is going to integrate to give me minus cosine of 3x minus 4. Now that's probably not going to be right, so I'm going to introduce just a coefficient in front, something that we want to find. So I think that the integral of this function will be this. Well, let's check that now by differentiating. So if I differentiate the function that I've got here, so if I say that this is my y function, if I differentiate that function, applying my chain rule, I'm going to differentiate inside the function first, which is going to give me 3, and then differentiate the function itself. Now cosine differentiates to minus sine, or we could say that minus cosine differentiates to sine, just as we wanted. I've still got my a value in here. Now I make a comparison. So my guess was almost exactly correct. All I need to do now is compare my coefficient, because I want 3 lots of a to be equal to 1. So in this case, we better let a equal 1/3. If a equals 1/3, we then know that our integral is going to be minus 1/3 of cosine 3x minus 4. And of course at this point we should not forget this is an integration, so we must involve our constant of integration, which is going to be c. Let's look at this example. Now this might not be immediately obvious, but remember from tables that tan will differentiate to give me sec squared. We can find this in the formula book. It's something that we should have in the back of our mind as being particularly useful. So again, I think to myself, what would be the best fit? What do I think this function is going to integrate to? I think this function is going to integrate to give me something to do with tan of 3x. Now that's probably not correct, so I'm going to just put a constant in front as my correction, and then let's check it. So if I differentiate this function, what do I get? Well, differentiating inside the function first, that becomes 3. Differentiating tan, I then get sec squared 3x. And again, I go back and compare, and I think, well, this is almost correct. I just require my 3a to be 1. So again, in this case, I need a to be 1/3. And if a is 1/3, I know that my integral is going to be 1/3 of tan 3x, and never forget plus c. Let's look at an exponential now. Exponential functions, we again should be able to guess at what these are going to integrate to. So my guess here is that this function will integrate to something to do with e to the minus 2x plus 1. Let's check by differentiating and see how close my guess is. If I differentiate this function, well, differentiating this to start with gives me minus 2, and differentiating e, I just get e, so this is a e to the minus 2x plus 1. Again, comparing my coefficients, this time I know that minus 2 times a needs to be equal to 1, so this is telling me that a must equal minus a half. And if a is equal to minus a half, I've then got my final answer, because this will integrate to give me minus 1/2 of e to the minus 2x plus 1, and again plus our constant of integration. Here's a slightly more complex example, but again, if I look at this, I can break this down into two functions. So I think about this function, and I think about this function. And I see that if I differentiate what's inside my brackets, I almost end up with what's outside my brackets. Almost. If I differentiate x squared plus 4, I get 2x, which is a linear term in x. So it would be safe for me to assume that I could use the chain rule to try and reverse differentiate this problem. So I think that this is going to involve something to do with x squared plus 4 all to the power of 3. And again, I'm just going to pop that constant in here. Okay, here's my guess. I've increased the power by 1. I've taken the original function inside, and I'm hoping that when I check this, when I differentiate this function, that I get something comparable to my integral. Again, let's do this by chain rule. So differentiate inside my function first gives me 2x. Differentiating my outer function is going to give me 3 lots of x squared plus 4 all squared. And let's just tidy that up quickly and move my constants to the front. So this becomes 6ax lots of x squared plus 4 all squared. Again, comparing my coefficients. This time I want 6a to be equal to 3. Notice that my x squared plus 4 all squared is exactly what I have here. So the only correction that I need is this 6a to be equal to 3. So in this instance I would let a equal 1/2, and I know that my integral is then going to be 1/2 of x squared plus 4 all cubed plus my constant of integration. Again, don't forget, you can check this at any point by trying to differentiate this. If I differentiate this, the 3 will come down and give this to the power of 2, and differentiating inside my function will give me 2x. The 2's cancel out, and I do end up with exactly what we've got in our integral. Now here's a nice example. This is something that we should have learnt from earlier in our course, perhaps C2, and that's a standard result that this will integrate to give us log of x plus c. Now remember, from C3, when we have been dealing with functions such as y equals log of 3x plus 1, if we wanted to differentiate this function, what we did was to differentiate inside the function first, and then put this whole function on the denominator of our fraction. This gives us a particularly nice result, because if I'm looking at fractions, if I can differentiate the denominator to get the numerator, then I know that what I'm dealing with is a log integration. Okay, so let's now go look at that in a bit more detail. And exactly as I was saying, if I look at this denominator, if I differentiate my denominator, I just end up with 2, which is a constant term, so I can use a different constant to try and cancel that out. So I think that because I can differentiate my denominator to get a constant term, it should be the same as my numerator. So my guess here is that this function will integrate to give me something to do with the log of 2x minus 9. Now if I differentiate this to check, dy by dx gives me, inside the function first, 2 multiplied by a over 2x minus 9. That's almost exactly what we've got here. Again, I do my comparison and I realise that I want my 2a, in this case, to be equal to 1. So again, I'm going to let a equal 1/2, and I know that this will integrate to give me 1/2 of log of 2x minus 9. Again, don't forget constant of integration. Okay, there are plenty of other nice examples of this, so let's just move down to the bottom here and think about the integral of, let's say, x over x squared plus 3. Again, if I look at this, if I differentiate the denominator, I'm going to get 2x, which is sort of what I've got in my numerator. So I think to myself that this function should probably be something to do with the logarithm of x squared plus 3. Let's check by differentiating. If I differentiate, I get 2x times a all over x squared plus 3. And again, I'm almost there. I just need to compare my coefficients. This time I want 2a to be equal to 1. So yet again, I'm in a situation where a must be equal to 1/2, not 1/3 if I was written there, 1/2. So my final answer here is going to be 1/2 log of x squared plus 3 plus my constant of integration. Okay, thanks for watching. The next video in this series is going to be on partial fraction integration. Okay, just don't forget, this is all about reverse chain rule. Check your integrals by differentiating.